Well, today, as I said, we're actually privileged to have two presenters. The first one is Dr. Wacław, also known as Wacek Swiech. Wacek got his master's degrees and PhD degree at the University of Wrocław, Poland. First one was working the phase transformation of ferroelectric materials. The PhD was in low energy electron microscopy. So Wacek has held academic positions at various institutions. After that, including the Technical University at Clausthal-Zellerfield, Federal Republic of Germany. After that, he spent some time as a postdoctoral fellow at the Max Planck Institute, Berlin, Germany. And then also in Germany as a senior research associate at Johannes Gutenberg University of Mainz. So in 1996, he joined the MRL as a research electron microscopist. Since 2012, he's a senior research microscopist, and he actually acts in two roles here. One under the electron microscopy core, where he manages some of our transmission electron microscopy tools. And the other one as co-managing the recently acquired atom probe tomography system. So Wacek has experience with the technique. He has looked at diffusion phenomena of lanthanum with erbium using field electron microscopy, a related technique, with two publications in 1986. The second individual who's going to present today, we're very happy to have here Dr. Timothy Spila, also known as Tim Spila. So he got his bachelor's degree in engineering science from the Penn State University, 1992. Got his PhD degree here at the Department of Material Science at the University of Illinois. He worked under Professor Joe Green and did investigation on surface roughening in compressed strained silicon germanium alloy thin films, especially using gas source MBE processes. Became a staff in the MRL 2004. He wears many hats here. He is responsible for our SIMS and TOF SIMS capabilities. He has been in charge about of our ion beam accelerator, where we do RBS analysis as well. And due to his extensive background in thin films, mass spectrometry, and CAMECA system, we actually asked at some point for Tim to be one of the responsibles for the newly acquired atom probe tomography system from CAMECA, which was installed in early 2019. So again, I know both Tim and Wacek are very busy with training and support the users, but we appreciate you guys taking the time to prepare this extensive review on the technique. So we're lucky to have you guys here today. Again, thanks for the time. Thanks, Tim. Thanks, Wacek. And I believe the first one to speak will be Wacek. Wacek, with that, welcome.
Thank you. So,
Daydream.
So here, I think Mauro wanted to show that, but instead I'm doing that. We have the extended number of different webinars. So you have a list here of the past webinars. Today we're talking about atom probe tomography, and the next week there will be the last one, as Mauro already mentioned a moment ago. So today the webinar is about atom probe tomography, and with this I would like to start with some presentation of insight into physical foundation of the technique, followed by description of sample preparation, which is very close to that of, partially at least, to that of focused ion beam technology, which was presented a week ago in the same series by Dr. Zhou. So first, I would like to give a big credit here, because we're talking after a real expert from the company CAMECA. So on the May 8th this year, Robert Ulfi had a beautiful description of the technique within the seminar series, Making the Best of a Bad Situation. It means COVID, characterization seminar series. organized by Penn State University and together with the University of Illinois, University of Wisconsin, and the University of Minnesota. So here on the bottom of the slide, you see the links where you could replay the recording of this webinar. So the same person, Robert Ulfik, is a co-author of the book shown on the left-hand side, book co-authored by David Larson, Ty Prosa, Robert Ulfik, as I said, Brian Geiser, and Tom Kelly from the CAMECA team in Madison, Wisconsin, about local electrode atom probe tomography, a user's guide. On the right-hand side, you see a similar book on the local electron atom probe from 2014, both edited by the Springer Verlag. So if you're very interested, just try to get a hold of one of these books. So at the beginning, I would like to present you kind of a slide of showing the different analytical methods, their analytical resolution versus detection limit. This slide comes from the Evans analytical group. You've seen probably this slide quite a few times because it's a beautiful compilation of every method. Here, as you see, shown by the red box, the atom probe belongs to elemental and imaging information techniques. So it's shown here on the upper left part of the diagram, which means that we have relatively small analytical spot size and extends down to some 10 to the minus 18 atoms per square centimeter. So this is a pretty sensitive method as well. So the spatial resolution is about 0.1 to 0.3 nanometers in depth and 0.3 to 0.5 nanometers laterally. Field of view is relatively small, 100, 200 nanometers laterally typically. This is a time of flight mass analysis of the emitted atoms from a specimen. Actually, they are ionized already. And the mass range is 1 to about 600 AMUs. The technique is very complementary to TM, which is shown on the diagram just next to it. So these two things happen very often. Many researchers try to complement one type of instrumentation with another. So the whole journey into the field emission techniques, field emission based techniques, started from about 1935, where Erwin Müller presented first field emission electron microscope, which was based on the Fowler-Nordheim equation, which was kind of a triumph of the application of newly developed quantum physics. So it was describing, as you can see on the left-hand side, the emission from metals related to the work function of the metal and the strength of the electrostatic field applied to the metal. So F, the electric field strength, is proportional to the applied voltage to the emitter and inversely proportional to the radius of the tip. So as you see on the right-hand side, right upper side, in most of the cases, actually in all of the cases, we're talking about very sharp needles as specimens. So here on the left lower side, we have the diagram, energetic diagram. The metal is on the left-hand side, vacuum is on the right-hand side. On the bottom, we have the solid state with the Fermi level on the top. With the work function difference, we can go into the vacuum level. So in the presence of very strong electrostatic field, the barrier, energetic barrier at the surface of the emitter is bent strongly downwards, and instead of going over the barrier like it would have been done in the thermionic emission described by Richardson-Dashman equation, we have a quantum process of tunneling of the electrons from vicinity of the Fermi level out to the vacuum. So this is described, as I said, by Fowler-Nordheim equation. On the lower right, you have the schematic of the FEM. So we have a sharp tip on the left, and there is a very high vacuum to keep the tip relatively clean over many hours if possible. On the right-hand side, we have a fluorescence screen. So you can see from this diagram that FEM is a kind of a projection microscopy. So the vacuum required is at least 10 to the minus 8 Pascal. The tip is, because this is electron emission, the tip is biased negatively with respect to the fluorescence screen. On the fluorescence screen, we see, for example, such patterns shown next to it in the circle. So this is a specific pattern emitted from tungsten oriented in 0, 1, 1 direction. You see certain map of different dark and bright regions. So in a sense, like in the Fowler-Nordheim equation, pattern visible on the screen is the a map of the work function projected onto the fluorescence screen from the emitter. So the central part is obviously here, as I say, the tungsten tip was oriented in 0, 1, 1. So this is the 0, 1, 1. Tungsten has a BCC orientation. These small dark dots on both sides, left and right, are 1, 1, 2 types of planes, and so on and so on. 1, 1, 3 would be on the top and bottom, and so on. So this is, in a sense, also a map of roughness of the surface, because for BCC metals, the 0, 1, 1 plane would be very flat. The other planes would be much more rougher, so they have a lower work function, appears brighter. So higher work function, dark, lower work function, bright. So here are a few stereographic projections showing the different lattices, so different geometries of the patterns which one can see. On the left-hand side, we have a cubic lattice oriented in 0, 0, 1 plane. So since this is 0, 1, 0, 0, 1 plane, this is a kind of a fourfold symmetry. You see the atomic planes represented by dots form a fold-fold pattern. In the center is a BCC lattice centered on the 0, 1, 1 plane. This is a twofold symmetric pattern, which you just saw a moment ago. Maybe let me show you again. This is a twofold symmetric pattern of the tungsten. On the right-hand side is, for example, like a platinum or something, FCC lattice oriented in the 1, 1, 1 plane forward. So this is a projection microscope. So already after the war, the same researcher, Erwin Müller, so he moved to the United States, and around 1955 came up with the higher resolution method compared to the field electron microscope, which had a resolution of about 2 nanometers. So this time the tip was even much sharper, so about 100 nanometers, 80 nanometers, 50 nanometers, very sharp needle. Tip was cooled to really low temperatures by liquid helium. And instead of vacuum between the tip and the fluorescent screen, there was some 10 to the minus 3 pascals of imaging gas, typically noble gas like helium or something like this. So this time, because we're talking about emission of ions, the tip was biased positively with respect to the phosphor screen. So the effect you see on the right-hand side is a beautiful pattern, again, of the tungsten 0, 1, 1 with the twofold symmetric distribution of these dots. These dots represent actually atoms. the planes are much smaller this time due to the different process of cleaning of such a tip. So so this was basically in those days. This was the very first atomically resolved technique. So one could see different atoms. Here are a few examples and maybe comparison between FEM pictures and FIM pictures again. On the upper left, we see this time nickel 001. Nickel is a cubic closed packed structure. And on the right-hand side from the FEM micrograph, we see a ball model of the tip. So the tip, in order to have clean areas to emit and show the structures, was annealed to relatively high temperatures, basically to the melting point of nickel. And therefore, we have relatively large facets. The front one is 001. There are on sides 113, which has lower work function, and so on and so on. The lower part of the left-hand side of the slide shows the FIM micrograph and the ball diagram of the same or similar tip. Now, as I say, in the field ion type of experiment. So the tip was cleaned by field evaporation rather than by annealing to keep the tip much sharper than in the case of FEM. So you see the beautiful resolution, single atoms everywhere, different planes, and this was used very often for different studies, like, for example, diffusion here at University of Illinois. On the right-hand side, you have a FIM picture of a tungsten 001 coming from not very long ago, from 2012-14. So you see the 001 plane in the center, the fourfold symmetric arrangement of all of these atomic positions. And in the very center of the 001 plane, you have a single atom of tungsten evaporated on the tip. So the study was to follow the diffusion mechanisms. So in this case, it was the exchange mechanism of the diffusion of the atom moving on the surface. So now let's move to atom probe. In the atom probe, we have also the tip from the shown on the left-hand side. Tip is cooled to really low temperatures, like 50 Kelvin or so. And then on the right-hand side, we have a screen. Actually, nowadays there is a position-sensitive detector, but in between we have vacuum, not imaging gas. So we're not obtaining pictures on the phosphor screen. We rather start emitting, field emitting atoms after ionization, and then the ionized atoms would move from the left to the right in the strong electrostatic field. So if the tip has a radius of roughly 80 nanometers, then detector is a typical channel plate size of roughly 80 millimeters. So we see that the arrangement has a magnification of about 1 million or something like this. So the atoms are field emitted, field evaporated by not only applying imaging field, but we have to go to the field evaporation, applying some positive charges, positive pulses to the tip, or small, very short temperature pulses to allow crossing over to the field evaporation. So the whole idea was done for the first time around 1967 when John Panitz, PhD student of Müller at the University of Mexico, put together a glass apparatus, whose schematic you see on the left-hand side. So on the top is the emitter part, mounted on some kind of a gimbal so that you could have chosen different atoms to be emitted. On the lower part, you have the screen with a hole in the center through which the atoms would be emitted down to the drift tube, and then the detector on the bottom would detect the presence of the event. So there was a main high voltage applied to the tip and the pulsar for field evaporation of a single atoms. So as you see on the right-hand side, we have a plot of a field applied to the emitter, or it represents also mechanical stress applied to the tip of the emitter versus the temperature. So the red dashed line represents a crossover for high probability for field evaporation. And in this case of Panitz, in the early times of atom probe, applied a voltage pulsing to go vertically from imaging area to the field evaporation area of the diagram. So if one changes the temperature from 30, 50, 70, 90 Kelvin, the voltage pulse required for field evaporation would be smaller and smaller, but the resolution would go less and less and less, smaller and smaller. So we here at the University of Illinois were very fortunate to have a Professor Gerd Ehrlich, who came from General Electrics in 1968. He was also working, like Müller, with the field ion microscopy. So on the left-hand side, you have a picture of an early instrument put together at University of Illinois. This was an ion microscope. As you see, everything was done with the glass. So all of the vacuum system was based on the glass mercury-driven diffusion pumps. And then starting from 68 to about mid-1960s, 1970s, he had a very talented PhD student, Rob Chambers, who put together the local for Illinois atom probe, so atom probe field emission microscope, shown on the right-hand side. This is the ion microscope part where he could have seen the patterns, and if he would turn the tip around, he could send the atoms down to the drift tube and analyze their time arrivals, giving rise to the masses and positions. So here on the bottom you see the picture of Gerd Ehrlich, and on the right-hand side is the PhD thesis copy of Robert Chambers. As you see on the top, it is dated 1975, so very early version. So this apparatus, as you see on the picture, was made in a full metal environment, but also driven by mercury charged diffusion pumps to get a very, very good vacuum, typically of at least 10 to the minus 9 to 10 to the minus 10 Pascal range. So now, sometimes people would like to not only apply voltages to the emitter, so go vertically to transition to the crossover line into the field evaporation, but also, as you see from the equation on the top, there is a certain probability of emission depending on the temperature. So instead of going vertically, one can get emission by laser pulses. This is laser mode of the atom probe. So here we showed just very briefly a copy from a paper by Udar of energy absorption maps, here calculated for aluminum tip, where for different wavelength of the laser, on the bottom of the diagrams would be the infrared laser, on the top UV laser, on the left-hand side for axial polarization, on the right-hand side for the transverse polarization. But the main thing would be to apply, to enhance the temperature to the very apex of the tip. As you can see from the diagram on the bottom right, pay attention please to the blue line, which corresponds to the UV laser, 360 nanometers. In the present instrumentation, we use the 355 nanometer line of the laser. So the most absorption happens in the very apex of the tip. That's exactly what we would need to cause the laser-induced emission. So again, a few words about the whole instrument. So atom probe, as you saw, is a combination of the projection imaging with a time of flight mass spectrometry. So on the left-hand side, you see the tip with all of these atomic layers. We would try to evaporate, field evaporate, atom by atom, all of the atoms down to some 150, 200 or more nanometers down to the tip by application of static, electrostatic field applied with some pulses to cause field evaporation. Time of flight would define the masses, because the smaller the mass and the higher the state charge of the atom, the quicker would be the event detected on the positive sensitive detector. On the right-hand side, you see just a few small lines of an equation. So the energy balance gives you the mass through charge state, which would be directly proportional to time. So if one plots, like on the upper right, the number of counts from the positive sensitive detector as mass to charge state ratio, one gets some peaks. For example, here, most probably a silicon tip with some boron doping. So you can demonstrate that you have 3 silicon peaks for single and for double charge silicons, and then boron double peaks for single and double charge borons. So this gives us the possibility of discrimination of masses. The position sensitive detector gives us insight to the position where from the atom was emitted. So both can give us a very nice combination of projection and time of flight spectrometry. So the position sensitive detector is composed of 2 elements: microchannel plate on the left-hand side, SEM picture, which is known to many people using imaging devices. It amplifies by a factor of 1,000 at least the number of incoming charged particles. Behind the microchannel plate, there is a delay line detector, delay line anode, composed of 2 snake-like wires placed at 90 degrees. When we have a hit of an ion into some location of the structure, the time difference from the left-hand side and right-hand side, or respectively the top and bottom, would give us the exact position where the atom or ion hits the screen. And then from the projection, you can go back to the tip and say where from the atom came from. So around 2000, Tom Kelly from now CAMECA team adopted the idea of proximal electrodes, which you see between the red part of the graph and then the positive sensitive detector on the right-hand side. This was called a local electrode. Such a local electrode, to which the emitting pulse is applied, allows for lowering voltages needed to field emitted ions, what in turn allows for higher data collection rates due to the lower voltages needed, allows also for higher mice resolution due to relative reduction in the energy spread from the voltage pulse, and finally allows for larger field of view, keeping the mass resolution kind of a constant. So on the left-hand side, there is a set of emitters. You will see that on the next slide in more detail. There is a small local electrode like a cone, and then the positive sensor detector on the right-hand side. The high voltage, the main high voltage is applied to the emitter or emitter sets. The local electrode has pulses, or in the laser mode, the emitters would be illuminated by a laser pulse. So here, there's geometry on the upper left, the tip on the kind of a goldish, and the local electrode on the right-hand side, LE. Model parameters for the calculation and mechanics would be like a 50 nanometer tip radius, 10-degree Schenck angle, specimen to local electrode distance, which would be required to permit about 70 degrees geometric field of view. And on the right-hand side, you have an optical picture of the local electrode on the right-hand side. Here is the cone of 70 degrees. On the left-hand side, on the middle slide in the upper row, you see a set of these small emitters. As I say, radius very, very small. Of course, not resolvable in the optical picture. And if you look on the lower part left, you see that we typically use something called a coupon, where we have the whole set of these emitters done by some lithographic methods. One of them enlarged on the very lower left. So on the top of such a post, we can place, typically by focused ion beams, a small needle to get topographic data from. On the lower right, you see the laser mode, the apex of the emitter illuminated by a laser, and on the right-hand side, the very apex of the local electrode. So the distance is very, very small. Here we have a few examples of leaps or local electron atom probe parts, typical for the company producing the machines, CAMECA. On the left upper side, the something called pack, which could be loaded into the vacuum. Emitter, a single emitter, or an array of these emitters. A coupon could be placed, like visible here in the middle upper row, into the pack. On the lower left, you have a photography of the loading area of the coupon into the some engagement part placed onto the pack. On the right lower side, you see that in a similar pack, one can replace or load into the analysis chamber a set of, actually, typically a few of local electrodes if they go wrong by a discharge or something. Here, finally, the photographs, actually 2 photographs of CAMECA LEAP 5000 instrument, very high vacuum in the analysis chamber on the lower left. This is at least 10 to the minus 8 Pascal, typically low 10 to the minus 9 Pascal vacuum. We don't have in our instrument the FIM option. So we only do the real atom probe, but no pictures of the tips. So counting electronics is attached, of course, to the analysis chamber. Tip cooling is not done nowadays by pouring a liquid helium into the dewar. It's kind of a similar to application of a cryogenic pump. On the right side, you see vertical small chambers. The top one is a load lock, where you load all of these packs inserted into the carousels. So you can store them in the lower part where you see the green light. This is a buffer chamber where all of these local electrodes and many tips organized by on different coupons and packs can be inserted into the analysis chamber. Magnetic linear rotation coupled manipulator allows moving these things into the analysis chamber. On the upper part, you have an inset which shows the kind of a covered version of the instrument, where you have only the load block and the buffer chamber, and of course on the lower, on the left side, the computer screen which allows controlling the whole process. So as I mentioned already many times, the sample preparation is related to making very sharp needles. So the specimens must be sharp with a radius of curvature of some 100 nanometers or smaller. And feature of the interest within the tip should be like 50 to 150 nanometers from the apex of the specimen. So one of the methods, traditional methods of preparing mostly metallic samples is done by manual electropolishing, where you could take a bulk sample, cut a small piece of a small chunk, which could be electropolished then to form into a very sharp tip. So this can be done by electropolishing in some electrolytes. Here is very briefly a diagram of that. So you put the chunk of material into the cuvette with the counter electrode, and you pass electrical current, typically the specimen connected to the positive pole, and then due to some motion of the electrolyte in the vicinity of the meniscus at the fluid surface, you have the thinning of this area, and finally the bottom part kind of falls down. You have to stop the electropolishing process immediately to keep the sharp tip. However, nowadays most of these tips for the atom probe are prepared by the FIB methods, which was actually shown already a week ago by Dr. Hongwei Zhou. So I'm kind of repeating this process for you. You start from a chunk of material typical for SEM. Then you have to put a protective layer of typically some platinum on top of it over the area which you will be removing for atom probe. Then you cut the wedge and clean this slab. Finally lift out a piece of the material, still with the protective platinum layer, and place onto the apex of such a post you have seen before. Finally, oops, not this way, sorry. You have to mount this thing and cut off the rest of the slab, and at the very end, with the annular or round beams, sharpen the tip into the very small radius required by the APT. Finally, you will repeat the steps number 3 and 4 a few times, because these tips can get fractured very easily in the during the process of taking data. So you would like to produce a few of them. So now we are presenting here kind of a set of 3 movies to show the process. So this is a ion beam imaging. So you cover the surface with a slab. You cut on the upper and lower part the trenches at some angle. You kind of clean this area. You cut some area around this slab, attach a micromanipulator tip by welding with the platinum to the right-hand side. You cut off the left-hand side, and now you are ready to lift the top of the slab out into the vacuum. So this was the protective layer deposition, wedge, cut, and lift out. This whole method is called lift out. Finally, you would like to move the slab into the top of the silicon post. So you see a needle from the left-hand side with the wedge slab attached, or being attached actually right now, onto the top of the post. So then this is the final step of attachment. And we have to separate a piece of material, so weld the slab onto the post, and then cut off the rest of the slab to do more of these steps for the preparation. We are left out with this some small chunk of material, which we have now to sharpen and polish. On the left-hand side is the side view, on the right-hand side is the top view. And here, this film is relatively quick, so I will try to repeat it in a moment. So this is the whole sharpening process visible on the left-hand side. Let me go one more through that for you. So sharpening, and then removal of the platinum layer, which is kind of a brighter on the top. You're left with the original material of the tip. So this concludes my part of the talk. And now we are giving the microphone to Dr. Tim Spila.
Hello. In the interest of time, I'm going to jump forward a little bit in my presentation. Wacek made a good comment about voltage mode and laser mode. This shows some of the differences that you could expect to see when you're using one or the other in our system. The voltage mode gives a higher positional resolution for the atoms than you can kind of see in the detector event histogram. But the voltage mode gives a better mass resolution. So that's nice. Depending on what you need, you can tune to one or the other. They do have a system that uses a reflectron in the ion path to increase the mass resolution in voltage mode, but that does drop the amount of atoms that you're counting from 80% all the way down to 50%, which may not be useful. Data modeling and analysis is done on a second computer in our system that is called IVAS. The analysis is started by creating a project file from the HITS data file. This is the first step in the IVAS wizard, which shows the parameters at the start of a measurement and any comments that were made during the run. One of the first choices made in the analysis is which portions of the data you want to do analysis on. This sample shows a nice smooth voltage increase, so the use of the whole file is warranted. But if there was a discontinuity in the voltage history, or you knew the region of interest was located at a specific place, you could work only with that section. Other drop-downs include mass, detection rate, background signal, etc. This is in step 3 of the analysis. You review the detector event histogram. You can actually exclude portions of the detector which do not produce data. For example, there's a mouse bite located just above the 3 o'clock position, which I've pointed out here, that you would want to exclude. Step 4 corrects for both the fact that the voltage is constantly changing during the measurement, the voltage correction, and that the detector is a flat circle instead of a hemisphere, which would be the bulk correction. Both of these effects will cause an incorrect timing of the ions reaching the detector, but these can be easily corrected in the software because we know both the X and Y position of the ion impact on the detector and the sample voltage at the time of the pulse. And so after the correction is done, which occurs in a recursive method, until the deviation in the full width half maximum is below a predetermined value. And so this is an example of a corrected spectrum which shows much higher mass resolution. In step 5 of the analysis, 3 or more peaks of known mass are identified in the spectra to produce a mass calibration. Generally, one of them is from the low mass region, one from a high mass region, and the third is somewhere in between. An initial calibration exists with the software to help you identify the peaks. A good mass resolution is important because small deviations can affect the identification and labeling of unknown or unexpected peaks. You'll note that in this plot, the y-axis is plotted on a log scale. So even small peaks in your spectra could be used to calibrate the x-axis mass spectra. The next step is tedious, but very important. It involves identifying and labeling each peak in the mass spectrum. Unlike SIMS, where almost all the peaks occur in the +1 charge state, atoms and small molecules in the atom probe spectra could come from a +1, +2, or higher charge state. However, there are no large molecules, and unlike SIMS, everything is ionized and can be counted. For example, if we zoom into the mass range from 10 to 35 AMU, we can see two sets of 3 peaks, which can be indexed for silicon, doubly and singly charged at 14 and 28 AMU respectively, and singly ionized oxygen and O2 at 16 and 32 AMU. Once all the peaks are identified, you can directly determine concentration for the whole sample or for a region of interest. Since the peak assignments can take a very long time, it is good practice to save the peak assignments in a separate file. They can then be used for reanalysis of this sample or as a starting point for other samples. Skipping peaks will affect your concentration and your 3D reconstruction because only identified atoms contribute to the reconstruction volume. However, the peaks above are plotted on a log scale, so the effect of the smaller peaks will only be important if you need really high sensitivity in your concentration profiles. The 7th and last step in the creation of the 3D model is the selection of model parameters. Suggested values are given, but may not produce the most accurate reconstruction. Key values are the image compression factor, the major elemental constituent of the sample, and the specimen parameters used to create the radius evolution. The simplest radius evolution is to use the voltage evolution. However, if you have images of the tip from an electron microscope, you can use that information instead. Each time you select a reconstruction parameter, you create a preview reconstruction. If the reconstruction is good, you can then save it with any appropriate notes you find important. You can also go back to the wizard, change the instrument or sample parameters, and create another preview. A 3D model reconstruction. This is a 3D model reconstruction of silicon pre-sharpened microtip. Both the 3D model and the mass spectrum use the same color model. So silicon is in blue and oxygen is in orange. And in this sample, as you can see, the majority is silicon with some oxygen near the edges. Can measure bulk composition calculated from the mass assignments, and it shows that it's over 99% pure silicon. This is a video highlighting the silicon and the oxygen measured in a different silicon microtip with a thicker oxide layer. As can be seen from the video, the oxide is located on the outside of the silicon post where the silicon oxide is formed due to air exposure. We have some examples from research groups here at the U of I. The first involves an examination of deformation in cast metallic glasses. The samples were then placed under compression, undergoing plastic deformation via the formation of a shear band. Combination of APT and TEM specimens were made from the samples along the shear band, such that the shear band should appear at the midpoint of the APT sample. In a sample with 2% plastic strain, you can see behind the red arrow, there is a compositional change at the location of the shear band. By constructing an ROI around the variation, the APT results show a change in composition across the shear band, where there's a decrease in copper composition and an increase in the aluminum and zirconium composition. In the sample with 4% plastic strain, TEM and APT results show crystallization in the shear band region. ISO concentration curves are created from the data to show areas of higher and lower concentrations. When you zoom in close enough on the crystalline areas, lattice planes can be observed in the reconstruction. Other APT samples in this series with lower strain did not show chemical inhomogeneity. The second example is of a proton irradiated 308L stainless steel sample. Of the 10 samples created, 1 showed a mixed phase with a grain boundary. The material is 308L stainless steel weldment filler. A rapid cooling is associated with the welding processes, creates a delta ferrite gamma austenite mixed phase microstructure. This specimen was then irradiated with 1 MeV protons to mimic fast neutron displacement cascade damage that would be seen in a light water nuclear reactor. The MRL atom probe was used to study precipitation and clustering of nickel, silicon, and other elements found in the 308L. The upper right panel shows an ISO concentration plot which highlights precipitates in the sample. There is also a grain boundary at the middle between the delta ferrite and the gamma austenite grains. 1D composition profiles show a difference in average composition in the 2 phases. 2 different clustering microstructures are observed. Number 1, approximately cuboid-shaped clusters in the delta ferrite, and number 2, loopy structures in the gamma austenite. From the TEM selected area diffraction dark field images, the cuboid microstructures can be indexed as G-phase particles, while the loopy structures do not show a distinct pattern and are therefore not a separate phase. Compositional analysis of the particles in the G-phase precipitates are consistent with the G-phase elemental composition, while the loopy structures do not show significant elemental difference from the bulk, which supports the conclusion that they are not a distinct phase. A third example from Illinois research groups involves using aluminum scantium as a model system to study precipitation and microstructural evolution of solid solution during annealing. Aluminum-3 scantium has a relatively small mismatch, about 1.6% with pure aluminum, while the scantium solubility in aluminum is very small, ranging from 8 × 10⁻⁵ at 200 degrees C to 1 × 10⁻³ at 300 degrees C. The goals of the study were: where do the precipitates form during intermediate annealing, and what is the role of grain boundaries on the diffusion and precipitation? To do that, they grew films with 1 to 2% atomic percent scantium and annealed them between 150 and 300 degrees C for 1 hour. TEM and STEM were used in addition to the atom probe analysis. The atom probe was used for determining the composition of the alloy, showing a desired concentration, in this case, of 1.3%. And measurements on an unannealed film produce highly randomized scantium locations, as can be seen from this reconstruction, where the black dots are the scantium, and the pairwise correlation function, shown below. STEM analysis shows that the grain size of the crystallites do not change during the annealing process. This is a plot of the APT reconstruction showing scantium in red and gallium in yellow. The aluminum has been removed for clarity. A thin gallium coating occurs during FIB preparation, and due to its fast diffusion along grain boundaries, it can be used to highlight the grains in the atom probe reconstructions, even though it's only less than 0.1%. From the existing diffusion data, the expected bulk diffusion of scantium and aluminum is expected to only be about 0.1 nanometer at this temperature. So diffusion along the grain boundaries is expected to dominate. A region of interest perpendicular to two grains across the grain boundary was constructed, and the concentration plot shows there is a very thin depletion region, about 2 nanometers, near the grain boundaries, in agreement with the assumption of grain boundary diffusion. Most of the scantium inside the grains is still in a supersaturated solid solution. Annealing at 300 degrees C produces a significantly higher diffusivity in the bulk, about 30 nanometers, and along the grain boundaries. The depletion region near the grain boundaries grows from 2 nanometers to approximately 20 nanometers, and there are scantium-rich precipitates that form there. inside the aluminum grains, the scantium is diffused and forms scantium-rich nanoclusters. To sum up, atom probe analysis consists of measuring the mass of field-emitted ions from a sharp tip. Spatial resolutions of 0.1 to 0.3 nanometers are possible in the Z direction and 0.3 to 0.5 nanometers laterally, with a field of view between 100 and 200 nanometers laterally. Mass of the ionized atoms are determined by time of flight between the voltage or laser pulse and the time of arrival at the 2D detector. Mass ranges from 1 to 600 AMU or more are possible, but most particles detected are single atoms. Since nearly 100% of the emitted atoms are ionized and up to 80% of the atoms are analyzed, the concentration sensitivity is only limited by the number of atoms collected and can be as good as parts per million. Atom probe is particularly suited for analysis of precipitates, grain boundaries, and isotopic variations in materials. I would like to thank you for attending this presentation and for all the previous presentations in the series. I would like to encourage you to come back next Thursday when Dr. Mara Sodelo will be presenting our last seminar in this series titled Top 10 Mistakes in X-ray Analysis and How to Avoid Them. You can register at go.illinois.edu/MRL webinars. If you have atom probe needs, feel free to contact Wojciech and me at the listed email addresses.
All right, thank you, Tim. Thank you, Wojciech, for this outstanding presentation. We have a few questions here. The first one is about sample charging. Do you need to worry about grounding yourself when actually handling samples due to charge built up, especially in dry winter air? Anybody wants to take that? Wojciech, Tim?
I think Wojciech's muted, so I'll say that in general, no. The samples themselves come on a little silicon coupon, and so those generally aren't a problem. And if you're dealing with wire samples, those will probably be conductive anyway, so charging generally isn't a problem. That being said, as Wojciech mentioned a little bit with the production of samples, the very sharp tip is very important, and static charge can have an effect. I don't know if he wants to say some more.
No, that's fine. So there's no problem really with the charging, unless there is a situation when the sample is non-metallic. But typically it can go very smoothly as well. So there have been atom probe runs on some, samples taken from moon rocks or something, and rocks. And then they went very, very, very smoothly.
Okay. One more question is that, can you explain, can you give more details why mass resolution gets lower in voltage mode?
That actually is not a hard one to explain. So in the voltage mode, you're pulsing the voltage on the local electrode, and the ion gets field evaporated, but that can occur slightly after when you apply the pulse. And so when the atom takes off can be delayed by a very short period of time, and that lowers your mass resolution.
But
okay.
If you would like to have, like atomic layers images in the reconstructed tips, then rather voltage mode would be actually better for imaging part of the business.
Okay. One more question is about sample damage that can occur during this process. Does it change chemical composition and quantification? I
mean, the immanent method feature is that you're consuming the sample. So the sample, like in the Sims process, the sample is being evaporated away. At the end effect, you have much shorter tip than you started. Everything that has been field evaporated has been field evaporated, and and there is nothing left over. Everything is on the detector. So you don't have what could be a problem with the contamination. and typically is related to the method of making these emitters by field focus ion beams.
Correct.
So then you typically using some gallium for cutting these small slabs and so on, and also sharpening the tip. So in very many cases, you have some amount of gallium at the beginning of the process, namely on the very apex of the tip.
One other advantage of atom probe over something like SIMS, in SIMS, not everything that gets sputtered away comes off as an ion, so you can't measure it. But with atom probe, everything that comes off the tip has to be ionized, and so you have the ability to measure it up to 80% because the detector isn't able to take everything in.
Good.
Channel plate mostly, the holes in the channel plate.
Okay. One final question. Can you give a little bit about comment about time scale of the experiments? Assuming everything is fine, I know there is a big difference between, depends on what you are analyzing, but like for FIB preparation, what's the typical time scale? And then once you load in once you actually doing measurements in the system, what's the time scale involved there? Is it a too slow technique, for example?
It is a relatively slow technique. Like, you know, the atom probe tip preparation by focus ion beams is kind of similar to that of TM sample preparation by FIB as well. So everything depends how skilled and experienced is the person making these tips. Can take maybe even half an hour or so, typically an hour or 2 or 3 per tip. So everything depends how skilled is the person. And then measurement also depends on how much of a tip you would like to reconstruct. So we had these experiments running up to, let's say, 24 hours, and then we would have analyze length of the apex of the tip as, maybe you can say as small, but still as large as like 400 or 500 nanometers. So 400 or 500 nanometers give you, let's say, 24 hours. Everything depends how a tip can take the high voltage. So sometimes you can go with a faster process. Sometimes you have to go really slowly because all of these forces apply to the tip. This is at the mechanical stress because you kind of ripping out the ions or atoms from the tip. So you can easily fracture the tip. You don't want to lose the tip. And that's what I mentioned as well. You would like to make a few tips to be prepared for the fracture of 1 or 2. Good.
Yeah, if I may add a little bit here, I mean, especially here in the MRL, for the sample preparation by FIB, we're in good shape because we have 2 FIB systems that can be used for that. I understand that nowadays the sample preparation by FIB is pretty much standard. It used to be like a kind of art by itself in the past where you had to count on luck, but now I think it's pretty much well established with the methods and recipes and protocols. For the instrument itself, as I see you guys operating it, once you load the sample, start actually collecting data, it's pretty much automated. And I think our software, our system allows for remote connection as well. So it can be a long process, but you don't need to be stuck in the lab during all that time. Correct me if I'm wrong.
Oh, yeah, you're right.
Yeah.
The only thing I would like to add is, as Wojciech mentioned earlier, doing microscopy on your samples can be very useful. And so that's one of the nice things of our FIB instruments. It's very easy to get some nice starting images of your sample. And it is even possible with a little bit of work to do TEM on samples as well. It requires a special holder, but we have the ability to do some of that as well.
Very good. So with that, any more final comments, team? Wojciech?
I'm good.
No, nothing here.
All right. So thank you
for
guys.
Attending.
Sorry?
Thank you for attending.
All right. Well, thank you both for the excellent presentation. Thanks everyone for the questions, for attending this webinar, for being with us through all this series here. Please don't forget next week, same time, noon, Central Time, let's talk of this series based on X-ray analysis. I see you guys then. I will be posting the video of this valuable presentation today soon in our YouTube channel. Hope to see you guys and stay safe. See you next week. Thank you. Bye-bye.